Imagine a machine that can backflip, climb stairs, and fold your laundry, all while weighing less than the average teenager. For decades, these humanoid robots were million-dollar lab experiments, tethered to the ceiling by thick cables. But something has changed. Suddenly, companies like Unitree and Agibot aren't just building one or two of these, they're spinning up assembly lines to build thousands. We are witnessing the transition from science project to consumer hardware. And the secret isn't just better AI, it's a radical shift in how we build the physical body of the machine. To understand this jump, we have to look at the price tag. A decade ago, a humanoid cost as much as a private jet. Today, you can buy a Unitree G1 for about $16,000. That's less than the price of a basic Toyota Corolla. This price collapse is happening because engineers have finally cracked the code of mass-producible mechanical limbs. By moving away from bespoke, handcrafted parts to standardized components, the EV Playbook is being applied to the human form for the first time in history.
In the past, robots like Boston Dynamics Atlas used hydraulics. These were incredibly powerful, but required complex pumps, valves, and high-pressure fluid that could leak everywhere. Modern humanoids have gone all electric. They use high-performance brushless motors paired with specialized gearboxes to mimic the strength and speed of human muscles. This shift makes the robots lighter, quieter, and, most importantly, much easier to manufacture at a massive scale, using existing electronic supply chains. But making a robot walk isn't just about power, it's about control. A humanoid is essentially in a constant state of falling, requiring thousands of micro-adjustments every single second. Every time the foot hits the ground, the mechanical joints have to absorb the impact while simultaneously pushing off for the next step. It's a brutal cycle for any machine. To survive this, engineers had to reinvent the very gears that move the robot. And that brings us to the most clever part of the whole machine, the torque density.
Think of torque as the turning force. To lift a human-sized weight, a robot's hip needs massive torque, but it also needs to be small enough to fit inside a slender leg. Standard gears would just strip their teeth or be way too heavy. The solution lies in two specific types of mechanical magic: harmonic drives and planetary gear sets. These aren't just gears, they are masterpieces of mechanical engineering that allow a tiny motor to move a 100-pound limb with the grace of a ballet dancer. If you opened up the shoulder of a robot like the Agibot Raise A1, you'd find a harmonic drive. This is one of the most brilliant mechanical inventions of the last century. Instead of rigid gears clashing together, a harmonic drive uses a flexible metal ring called a flex spline. It actually deforms into an oval shape as it spins. This allows almost every tooth to be engaged at once, providing incredible torque with zero backlash, that annoying wiggle you get in cheap gears. But harmonic drives are expensive to make. So, for the heavy lifting in the hips and knees, manufacturers are turning to planetary gear sets, similar to what you find in an automatic transmission. By spreading the load across multiple planet gears, these systems can handle the massive forces generated when a robot jumps or carries a heavy box. The genius here is in the manufacturing. These gears can now be mass-produced using high-precision sintering, where metal powder is pressed and heated into a solid part.
However, all that torque creates a new enemy: heat. When a motor is fighting gravity just to keep the robot standing, it generates a massive amount of thermal energy. Engineers solve this by using the robot's own metal frame as a giant heat sink, drawing warmth away from the motors and into the surrounding air. Some designs even use active cooling, tiny high-pressure fans, or even liquid cooling loops hidden inside the limbs to keep the electronics from melting. The result is a power-to-weight ratio that finally rivals biology. We are now building machines that can move with the same peak power as a human athlete. But there's a catch. While a human can heal, a machine only wears down. Every step taken is a step closer to mechanical failure. To fix this, we have to look at the material science of tendons and how they handle the stress of a 24/7 industrial environment. The transition from lab to factory floor means these robots can't just work for an hour. They have to work for years without a break. This requires a level of reliability that we've only ever seen in the automotive industry. And that's exactly where the next breakthrough is coming from. By treating a robot like a car on legs, we are finally making the mass-produced humanoid a reality. To keep costs below $30,000, manufacturers are ditching custom parts for modular assembly. The same arm used on the left side is mirrored for the right. The leg actuators are identical to the arm actuators, just scaled up. This Lego brick approach to engineering allows for massive volume discounts from suppliers. It's the same strategy that made the smartphone and the EV affordable, and it's now being applied to the most complex machine of all. But even with perfect assembly, there is a hidden challenge: mechanical tendon fatigue. In humans, tendons are elastic. In robots, they are often rigid steel or carbon fiber. Every time a robot's knee bends, these tendons experience microscopic stretching. After millions of cycles, the metal atoms actually begin to pull apart. This leads to joint creep, where the robot loses its precision and eventually suffers a catastrophic failure mid-stride. To fight this, material scientists are developing new shape memory alloys, metals that can deform and then return to their original shape without weakening. These materials act like a mechanical fuse, absorbing the shocks that would otherwise shatter the expensive gearboxes. By solving the fatigue problem, we are moving from robots that can work to robots that do work, reliably for years on end. The implications are staggering. Once the hardware is cheap and reliable, the only limit is the software. We are building the universal computer for the physical world. Just as the PC moved from the office to the home, the humanoid will move from the factory to the street and eventually into our houses. It's not just a machine, it's a new type of infrastructure, a physical platform that can be programmed to do almost anything a human can do. So the next time you see a video of a robot doing a dance or a backflip, don't just look at the movement. Look at the joints. Look at the clever engineering that allows a few pounds of metal and silicon to mimic the complexity of 4 billion years of evolution. The era of the million-dollar prototype is over. The era of the mass-produced humanoid has begun, and it is absolutely brilliant.